Many people who look at meteorites think that Earth is a target Earth. Well, it isn't really a target. It's just accidentally in the way. There are rocks buzzing around all over the place. Every week or two on Earth, a visitor from space enters our atmosphere and blows up. Friction, impact with the dense atmosphere. They're coming in at velocities of, well, a slow one may be going as slow as 10,000 kilometers an hour. A super fast one, perhaps 80 or 90,000 kilometers an hour. At that speed, the air feels very dense to them, and they'll get down into the atmosphere maybe 30 kilometers above the ground, maybe as low as 15, and blow up. Well, we have a lot of evidence for meteorite impacts on the ground, and it doesn't come just from the meteorites themselves. In fact, other lines of evidence are every bit as important, particularly the impact craters that I have listed here, then meteorites, of course, and then some objects you've probably never heard of, tectites. We need to define some words. I call these the 3 M words: meteoroid, meteor, and meteorite. In general, the media get these all mixed up. A meteoroid is a small asteroid. That's a name you probably already know. An asteroid, a rock in space, mostly refers to rocks in our own solar system, too small to be planets, and for the most part smaller than any of the moons as well. So a meteoroid then is an asteroid with a diameter of less than 50 meters. A meteor is not an object. A meteor is an effect in the atmosphere caused by an incoming meteoroid. There are two things involved here. First, the air gets hot due to friction and glows. The friction itself causes the surface of the meteoroid to melt, and thus it glows too. To get an idea of the sizes, a meteoroid the size of a football will make a meteor the size of the football stadium. In that way, a meteoroid the size of a small car can be seen as a meteor all the way from Winnipeg, say it comes in over Saskatoon. You'd see it in Winnipeg, you'd see it in Edmonton. Meteorite, material from a meteoroid that makes it to the ground surface, such as this 500 gram piece of buzzard coulis. The individual pieces are called meteorite fragments, although we often get sloppy and just call them meteorites. But really the word meteorite refers to the whole collection of fragments that are left over from that meteoroid. There are over 300 impact craters on Earth. There are 22 craters bigger than 8 kilometers wide in Canada, 3 of those in Saskatchewan. There are actually 7 impact craters in Saskatchewan, but the 4 in the south are all buried. The impact was long enough ago that sediment has been washed in, completely filled the craters up, and there's no surface indication of them at all. They've been found during the drilling for petroleum. The 3 in the north, however, can be seen. The Carswell one in the far northwest there is the biggest, but you can't get to see it. You can't even identify it flying over it. The Gow Lake is a very nice one, but it's only 5 kilometers, and you can't very well get to that one either without a float plane. But the Deep Bay crater right here, you can drive up fairly close to it. You can drive up to the town of Southend, rent a boat, and you can go fishing in this crater if you want to. All right, the south end of Reindeer Lake, this 125 kilometer long lake in Saskatchewan, and a little bit of Manitoba. The crater itself is about 13 kilometers wide. The rim of the crater, you can't see it on the photograph. You can see the lake, what partly fills it. It's an 11-kilometer diameter lake. And it's partly filled with washed-in sediment. The impact was 100 million years ago. So we can't see this central dome. It's buried under the sediment at the bottom. And then, of course, that's buried under this lake. I once canoed around the lake, took all day. But Earth is not the only place with impacts. Mars has impacts, Venus does, Mercury does, and especially our moon. Not much of the moon's surface is impact-free. Based on the proportion of free metallic iron, the iron meteorites have over 90% iron. Almost all of them have over 90% iron. But they have other things with them as well, particularly at least 4% nickel. Every iron meteorite has nickel. A few have as much as 20%, but mostly it's around 7%. Then there are other elements present, like carbon, maybe a little sulfur, oxygen, silicon, even a little bit of gold, and some other trace elements. Two pictures of irons there, one called Sokoty-Yelin, blew into eastern Russia in 1936, and Campo de Cielo landed in Argentina. Well, we don't know when it landed. It was found by Spaniards in the early 1500s, but that's according to the Spaniards. The local people had been using fragments of this to make iron tools out of, arrowheads, for centuries. We don't know when it landed. Stony meteorites, most of them have a bit of free metallic iron. Some have none, and they rarely have more than 20%. Most of them lie somewhere in the 15 to 20% range. This is a big piece of the buzzard coulis. It has almost 20%, about 18% iron in it, enough that it will attract a magnet. These are some smaller bits of buzzard coulis. That's a 1 centimeter cube right there for scale. And these are two other little pieces of buzzard coulis, both of which will be attracted to a magnet. The last type of meteorite that we'll look at the moment is the so-called stony iron. Now, approximately 50-50, but it can vary from 70% iron, 30% stone, to the opposite, 30% iron and 70% stone. Most of them, when we cut them open, look something like this. They'll have a yellowish to yellowy green mineral, which is a mineral we call olivine. We have olivine on planet Earth as well. And then that's all mixed up with that silvery stuff, which is the iron. The last object on our list of things that result from impacts, craters, meteorites, and tectites. Well, tectites are small glassy objects that form when an impacting asteroid, typically well over a kilometer in diameter for the asteroid itself, melts some of the Earth target rock. Then as the object explodes on the impact, it splashes that molten Earth material out, which freezes as it spins through the atmosphere and ends up forming this glassy stuff. Even Mars has meteorites. The Mars rovers that we've sent up, there have been 4 up there, three still working. Well, one went up just a couple of months ago. This is a cartoon here of a fine painting, I should say, of one of the rovers running into an iron meteorite. And they've found about a dozen or so of them, just accidentally. One of these rovers might run a kilometer in a year and run into 1 or 2 meteorites in that period of time. The surface of Mars appears to be just littered with iron meteorites. Well, once they're there, if they've fallen any time in the last 2 billion years since Mars lost its water and most of its atmosphere, there's been nothing to rust them. They just sit there. So here's the biggest one that was found so far, about 2 meters long. A smaller one right in front of it, that's not quite a meter. And these pictures are pretty much the scale here. And this is the smallest one, I think, right there. It's maybe not quite 20 centimeters to the side. So lots of iron meteorites on Mars. I'm going to take a brief look at some of the most famous meteorites with you. Perhaps the most famous is one called Murchison, fell in 1969 in South Australia, well, in Victoria actually, the southern part of Australia. And also Allende, which fell in Mexico the same year, about 6 or 7 months apart. Murchison, along with Allende and with several other of the carbonaceous chondrites that have been analyzed, contain organic compounds. Now, an organic compound doesn't mean life. It doesn't mean that there's anything biological there. An organic compound in the world of chemistry is anything that is made of a mixture of carbon, hydrogen, oxygen, and nitrogen. Well, that's what we're mostly made of. And that's what all life forms are mostly made of. And that's what a thing called amino acids are made of. Amino acids are the base unit of all life on our planet, and presumably will be the base chemical unit for any other life we manage to find in our solar system, should we ever find any. Now, so far, 70 different amino acids have been found in Murchison. Some of these are the same ones that occur in Earth life forms. This presence of these amino acids in the carbonaceous chondrites appears to indicate that the building blocks of life occur throughout our solar system, perhaps even the rest of the universe.